Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Olaoluwa, and I've been walking you through the physics course. We'll be talking about pressure today, and we'll be looking at pressure in liquids, in fluids generally. We'll consider the topics, the subtopics, the concept of pressure, pressure in a liquid, the application of pressure, that's the knowledge of pressure, how do we apply it in our everyday life. We'll consider atmospheric pressure, the simple barometer. We'll consider also the practical use of a barometer, various units of atmospheric pressure, and we'll conclude with pressure devices. So, let's start. What is pressure? Many times we hear people talk about them being under pressure and things like that. Well, pressure is something close to that. Pressure is simply a kind of force, a force acting on a particular body per unit area. So pressure can be mathematically expressed as P equals F divided by A, where P here is pressure and F is force, A there is the area. Now, whatever the area across which the pressure is being exerted, that's what will be considered as the area. It is possible for the area to have different formulas. It can be a circle, and when it's a circle, of course, the area of a circle is pi r squared. If it is a square area, it is L squared, and if it is a rectangle, L length times breadth, and all other shape as that. In a few seconds, a question will pop up on your screen to test your knowledge of what has been taught so far. Welcome back. Earlier I told us about pressure as the force acting on a particular body per unit area. Well, force in liquids is not calculated the same way force is calculated in solids. Yes, of course, when you are exerting a pressure on a liquid, that pressure is the same. But when a liquid is exerting pressure on something inside a liquid, that there is a little difference. Yes, it is still the same thing in the sense that the formula still remains pressure is still force over area. But the area this time around, when it comes to liquids, just imagine it. I have a bucket of water, it's filled, and I drop maybe a particular thing, an item into it. Let's say I drop a stone inside it. Now, apart from the atmospheric pressure, which was initially acting on the solid, there is another extra pressure that would be acting on it now. And that pressure is due to the weight of the water above the solid. The water above the solid, that is the liquid that is in the container above the solid, would exert its own weight on the solid. It's just like saying I'm standing and then I carry someone else on my shoulder. Of course, I'll definitely feel the weight of the person I'm placing on my shoulder. So the stone underneath the water would feel the weight of the water above it. So thus, of course, we know that weight is a force. So we can switch our force here for weight. That's the weight of the body. And of course, we know W, weight is mass times acceleration due to gravity. So we can bring that in, and we'll have our pressure, which equals weight over area, to be equal to mass times acceleration due to gravity divided by area. So our weight is equal to mass multiplied by acceleration due to gravity, and when it is introduced, we have mg divided by a. Sometimes you can have problems when you're working with mass. But we know definitely that mass is always equal to density multiplied by volume. We can always be sure of the density of the water or the liquid in question. We don't usually work so much with the mass of liquids when we are working in physics. We would rather work with the density because it gives us a value that is more concrete, much easier to work with. So, with the density and volume now, introducing that into the equation, that's taking away m, we now have our new expression to be, our new formula would become, take out mass and you put both of them, that's density multiplied by volume multiplied by acceleration due to gravity divided by area. Bringing in our volume into the equation now, we would have density multiplied by AH, since our volume, we have it here, is AH, multiplied by G divided by A. Oops, we have A and A. A can cancel out A, and our final formula for calculating density, for calculating pressures in liquids, or generally in fluids, not just liquids, you can use it in gases, you can use it also in liquids, would be density multiplied by acceleration due to gravity. Let me write that again so it can look, G multiplied by the height, that is the height of the water above the solid which is immersed in the water. So in this particular condition, this is the height in question. So when we're calculating the pressure at this point, if there were to be no additional pressure acting, for now we will not worry in our head about atmospheric pressure. When we get to that point, we'll start considering it. So the pressure exerted by the liquid on the top of the solid which is thrown into it would be the density of the liquid multiplied by acceleration due to gravity multiplied by the height of the liquid above the water and the solid that has been thrown inside it. The formula for the unit for pressure, where when it comes to units for pressure, we have several units that we use to represent pressure, but this SI unit for pressure, that's the international standard unit for pressure, is in Newton per meter square. Newtons per meter square. Of course, you know newtons come from pressure and from force, and meter square come from area. And if you want to confirm whether this our formula would get there, I'd like you to try that. Let's see. We'll look into that later in the lesson. What are the applications of pressure? Of what essence, of what benefits is the knowledge of pressure to us? Pressure is one of the most important things that science has ever discovered. It has helped us in the designing of so many machines. One of the most common ones is the hydraulic press. In fact, let me just use the word hydraulics generally. Hydraulic machines. All hydraulic machines use the knowledge of pressure in their operation. For example, a very good example of an hydraulic machine which I know you can easily relate to is your hydraulic, car jack. The one I know you can always easily relate to is your hydraulic car jack. Of course, I know many of us have seen vehicles break down, and we've seen people try to lift their vehicle to change their tires. The car jack, you just need to paddle a little, and as you paddle, it starts to raise the vehicle up. You exert just a little force. One man and that small machine would lift a whole car up. Like, wow. So it simply works with the principle of pressure. Another thing, okay, let me give you an insight into what this principle, that aspect of it. It has to do with the law according to Pascal. Pascal's law of pressure says that the pressure exerted by a liquid is distributed uniformly at every point in time. So, inside your car jack, what you are seeing happening is something like this. There is a region, there is a liquid inside the whole thing. Well, it is not exactly as I'm drawing it, but that's the concept. There's a liquid in the whole thing, and the liquid, of course, would be at the same level on both sides, since the pressure inside the liquid is the same. Now, air is just like a space, nothing there. This is where you place your load. So the load of your car is actually like air, probably 1 meganewtons. But here you have your paddle that you're just using to paddle, and you're maybe probably exerting like 10 newtons. The radius of this place, or let me use radius now. The radius of this place, since of course it is very narrow, it can be as small as, say, 2 centimeters, while this one may be as big as 10 meters. Of course, the formula for pressure says pressure equals to force divided by area, right? So, using this, I told you the pressure here equals to the pressure here. Since the pressure is equal, that means at this point, I can actually exert a small force here. But what force would I experience here? I don't want to use, but I want us to calculate how much force will be transmitted from this point to this, working with this particular parameter. So we will know whether we can lift our proposed 10 meganewtons. So let's keep our 10 meganewtons somewhere. We want to lift 10 meganewtons. Let's see if we can generate something enough from this particular setup. So, converting first, of course, all our units must go to the same. That is, our centimeters must go to meters, and 2 centimeters is 0.02 meters. So, let's write out our parameters. Here we have, let's call this F1, and we'll call this the R1. So F1 is 10 newtons, R1 is 2 centimeters, which is the same thing as 0.02 meters. On this other side, we are looking for F2, and we know our radius to be 10 meters. All right, let's go. So what do? We don't need radius. We need areas. But we can manipulate and work out something while we're working. We know that area would be radius squared, that is pi r squared. So we can just use the formula since we're talking about circular shapes. So pressure will be equal to F1 divided by A1, which will be F2 divided by A2. Our F1 is 10. Our A1 is going to be pi times 0.02 squared. Our F2 is unknown, and our A2 is going to be pi multiplied by 10 squared. Of course, when you cross multiply this pi, we cancel out this pi. So our F2 would now be equal to 10 multiplied by 10 squared, which is 100, divided by 0.02 squared, which is 0.0004. And when you press your calculator to get the answer, we have, when you press your calculator to get the answer, you have 2500000 newtons. This is about 2.5 meganewtons. Wow. Well, that means our design was not good enough. But we can also work on it. We can reduce this to maybe 1 centimeter. It would increase even the more. So you can imagine the kind of effects reducing one side for the benefit of the other side can be. Now this is one of the many applications of pressure. Even though our original intention was to get 10 meganewtons, well, this our machine can't go that far. We can only get to as much as 2.5 meganewtons. But I'll challenge you. Why don't you try and see? Design, look at it, what do you think you can alter and get up to 10 meganewtons. You can try that as we consider other things. Okay, let's consider atmospheric pressure. We've talked about pressure. We described pressure as the force acting per unit area on a particular body. And this time around, we're talking about atmospheric pressure. So the word atmospheric comes in as relating to atmosphere. We all know that the atmosphere is that part of the earth where the air is occupying. So when we go out to outer space, we know outer space contains vacuum, which is actually nothing, and you start coming into the field, into the gravitational zone of the earth, and then you begin to come in contact with air. That is our natural air which we breathe, and the air is thinner at the beginning, and then it gets thicker and thicker and thicker, and eventually it gets to where we are today, where we are right now on the earth. It should also be noted that air itself is matter, which means it has its own weight, just like in the case of the liquid we discussed earlier. So air is exerting a certain amount of weight on us, and the atmosphere is several kilometers high up above us. So we have several kilometers of air actually compressed above our heads. Therefore, because of the weight of this air above us, we are experiencing what is known as the atmospheric pressure. When you move on from regions of low altitudes, that is from low grounds, when you move to regions of high altitudes, that is high grounds, islands, such as mountains, the pressure on you is reduced. Of course, because the air above your head is less. But when you are at low altitudes, the pressure on you is higher. Now, if you should go into lower altitudes, the pressure on you will be even further higher. That's why many of us, when we do travel and we climb mountains and climb hills, some of us do have this kind of feeling inside our ear, like something is going wrong. So you have to yawn for your ear to balance out the pressure. Yes, you're experiencing changes in pressure. Also, when you go deep in water or in any liquid, pressure is increased. Pressure is controlled by several properties, such as the density of the fluid, such as the depth or height, altitude, and also pressure is equal at all levels. If it is in a particular, if it is in air, if the ground level is equal, the pressure will be equal at both sides. If we are at a particular altitude, let's say you are on a particular mountain and I'm on another mountain in another location, but we are at the same altitude, the mountains are both 300 meters high, the pressure exerted on me where I am will be the same pressure exerted on you at the location where you are. So that is atmospheric pressure. Pressure has several units. We talked about one of them earlier, which is the standard unit, that is Newton per meter square. Other units are Pascal, atmosphere, and interesting units like millimeter of mercury, millimeter of water are also used as measurements scales for pressure. So why do we do such comparisons? Well, in a laboratory, when we're working with different kinds of fluids and fluids having different densities, we prefer to use certain fluids and set them as standards. And mercury happens to be one of those fluids. Of course, water is readily available, so it happens to be one of those fluids also set as standards. But recognized, internationally recognized standards, internationally recognized units are Newton per meter squared, Pascal, and bar. Where bar, the relationship between these three, even atmosphere is not been officially in complete use. The relationship between these three is 1 Pascal equals to 1 Newton per meter square, while 1 bar equals to 10 raised to the power 5 newtons per meter square. Taking a look at all the formulas we have, in physics we work with Newton per meter squared and Pascal because those are kind of like pressure ranges that we do really like. But the atmospheric pressure of the Earth is actually 10 raised to the power 5 pascals. That's like very big. We, the weather forecasters, the meteorologists, that's the weather scientists, they prefer to work with what they call bar. They call it 1 bar, and that is like 10 raised to the power 5 of what we work with in physics. So it is interesting to know 1 bar is the bar thing is it is interesting to know that the unit bar finds its use very much. Is it good? Okay. It is interesting to know that the use of bar is very much common to the field of metrology. While in physics, we work with Newton per meter square, we work with pascals. And also, this same unit, which is 1 bar, is also the same thing as 760 millimeter of mercury. And that is the pressure, the atmospheric pressure at the sea level. Okay, let's look at the barometer. The barometer is a tool that is used to measure pressure, especially atmospheric pressure. This diagram on the board shows a description of what happens inside the barometer. We see on the board here, I'm having a bowl, and I'm indicating that the content of the bowl is mercury. And I'm having 2 tubes inside the bowl. Actually, in the real sense of it, what I did was tilting this. It's just one test tube. It's just one tube, one meter long glass tube. It was filled with mercury, then slowly placed in so as I won't allow air to be trapped inside it. So to avoid air being trapped, the top was covered, and it was slided into the bowl of mercury and then raised to stand erect. Of course, you can see that at this particular point in time, the entire glass tube was filled with mercury. But when it was made to stand erect, mercury kind of like, that is, it's came up to stand erect, and all of a sudden the mercury dropped. And if you notice this drop, this place that you see here is being occupied by vacuum. It's been occupied by vacuum. That is nothing. It is actually empty. Not even air is there. So what happens to the mercury? It simply is responding, it's taking a measurement of the pressure in the atmosphere. That is the atmospheric pressure. How is this done? Remember when I was talking about I talked about Pascal's principle earlier. I said in Pascal's principle, Pascal said that the pressure is uniform at every point in a liquid. So the pressure at this place is equal to the pressure at this place, which is also equal to the pressure at this place. Now, it was also noted that at 760 millimeters, that was the point to which the mercury did drop back to. That is about 0.76 meters. So that's why we say the atmospheric pressure can be measured as 760 millimeter of mercury. I made mention of millimeter of mercury a few minutes ago. So how do we now calculate it in Pascal? That is in newtons per meter squared. How do we know what that is what? Remember, I gave you a formula for how to calculate pressure exerted by a fluid on a body, and that was given as P equals rho G H. Rho G H. We know that the density of mercury equals 13,600 kilogram per meter cube. 13,600 kilogram per meter cube. And of course, we know our acceleration due to gravity, G. We have always been taking it as 10 meters per second. And now we are having our height. 10 meters per second squared. And we are having our height to be 0.76 meters as measured from the experiment. So let's put all of them together. That's 13,600 multiplied by 10 multiplied by 0.76. When you multiply this, you would get, using your calculator, you would get 103,360, and it is in Newton per meter squared, or you can say in pascals. So that gives us the atmospheric pressure of the Earth at the sea level, and this is what is described as 1 bar. It is yes. This is what is described as 1 bar by the meteorologists. It is approximately 1 bar. What are the uses of barometer? Why is a barometer important? Of course, we know it is used for measuring pressure. So why do we need to know what pressure is? First and foremost, it helps in weather forecasts. It helps in making forecasts of what would happen, whether it would rain or not. Also, It can be used to determine the altitude at which a plane is flying, or it can also be used to determine the height of mountains, the altitude, the heights. It can be used also to measure. The knowledge of pressure is also very, very important in the health sector. Not only in our conventional machineries. The importance of it in machines cannot be overstated. You pump your tires, you need to check it. You need to check how much pressure, if the pressure is enough or not. So these are some of the applications of the barometer. Okay, let's consider some of the application of pressure in our day-to-day lives. On your screen right now, you'll be seeing a medical syringe. For one to use the syringe to inject a patient, you need to pull the piston of the syringe back. Of course, after putting the needle into the drug, you pull it back to pull into the syringe, into the tube of the syringe, the liquid, which is the thing you want, the medication you want to inject into the patient. And also pushing on the piston compresses the liquid with a pressure into the person, into the patient being injected. We see this, the syringe itself works with the principle of pressure. We see the same thing happening in your bicycle pump or your tire pump, where you use your manual pump. The air is being pulled in and is being pushed from inside the barrel of the pump into the tire. Now there is a valve at the tip of the tire tube that stops the pump from pulling the air back out of the tire tube. So when you pull the piston once again, instead of it pulling air from the tire, it pulls air from the atmosphere. And when you compress the piston, it pumps the air into the tire tube. And that's how we get to pump our bicycle tire. The same principle applies also in the manual pumping machine. The manual pumping machine, normally called manpower. It also has a stopper and a valve. This principle of pressure, the understanding of pressure, has made life very easy for man. Today, we can do so much with the knowledge of pressure. In this topic, we have considered pressure in fluids. We talked about the concept of pressure, where we define pressure as the force acting per unit area on a thing. We talked about pressures in liquid, and we gave the formula for calculating pressures in liquid, which we gave as P equals density, that is, pressure equals density multiplied by acceleration due to gravity multiplied by the height of the liquid above the point where the pressure is being exerted. Pressure also can be measured as force divided by area. We talked about the applications of pressure in hydraulic devices. It is used also for measuring relative density of liquids. It is used in very many things. In fact, we talked about one just recently, pumping of our car tires, designing of very many machinery. We talked about the barometer. We talked about atmospheric pressure, and we explained it that the atmospheric pressure is due to the volume of air and the weight of the air that is above us. And we discussed the barometer. We explained that it is an instrument used for measuring pressure. We talked about different volume units in which pressure can be measured. It can be measured in newtons per meter squared. It can be measured, 1 Newton per meter squared is also equal to 1 Pascal. And we talked about 1 bar. We explained that 1 bar equals to 10 raised to the power 5 pascals. And we talked about other units such as millimeter of mercury. We said, of course, atmospheric pressure is 760 millimeter of mercury, and which is also the same thing as 10.3 meters of water. And we also discussed briefly different types of pressure devices, such as the syringe, our siphons, bicycle pumps, manpower, that is your manual water pumping machines. In a few seconds, some questions will pop up on your screen. Please attempt them. And if there is any question that is giving you a problem, you can review this video one more time.